What is big O notation in programming and how is it useful? Like, what's the point? I was first introduced to the big O concept back at university in undergrad, and initially I found it rather vague and a little bit confusing. Like, why can two algorithms that run at different speeds have the same O notation? Let's back up a little bit and start from the beginning. So in programming, big O notation is an indication of what happens when you increase the amount of input data that an algorithm has to process. For example, if we double the amount of input data, how much longer will that algorithm take in order to process that data? The technical term is time complexity, although you can also use it for memory complexity as well. Does that sound complicated? Stick with me because the core concept is actually quite simple once you get it. So let's look at some examples. Say we have an array of numbers and we want to read just one number out of that array. It doesn't matter if this is a big array or a small array. Ignoring things like CPU caches, this will always take the same amount of time. And we denote that with big O and in brackets 1 for constant time. Now let's say that we want to sort the same array from smallest to biggest, and we use a naive sorting algorithm like bubble sort. That has big O n squared complexity. So as you increase the size of the array being sorted, the time taken increases quadratically. You double the size of the array, you increase the time taken by a factor of 4. And clearly that is a big problem when you have a very, very large array. By contrast, if you use a better sorting algorithm like quicksort has an average time of O n log n, which is clearly way better when you're processing a lot of data. So it pays to choose the right algorithm. And I learned this the hard way at university when we were given an assignment to process a 2D array. I cannot remember the details of the task. I just remember that we had to process arrays up to 5 by 5. And I thought, oh, just 5 by 5, let me brute force it. Bad idea. So 2 by 2 worked great, 3 by 3 in an instant. When it got to a 4 by 4 array, it took several seconds. And when I went up to 5 by 5, it basically didn't finish. I think it would have taken years to process one 5 by 5 array. What went wrong there? Why was the 5 by 5 taking so long? So the brute force algorithm had O n squared complexity. So it was increasing, the time was increasing quadratically with the size of the array. You might think, yeah, but you only went up to 5. However, remember, it's a 2D array. So n is not 5. A 2 by 2 array has 4 elements. A 5 by 5 array has 25. So not only is it an O n squared algorithm, but the input size was increasing quadratically as well. And I discovered this the night before it was due. So I was in a bit of a panic, and I am truly grateful to the classmate who showed me an algorithm that could do the same thing in big O n log n time. Phew, saved my butt. This incident also explains why two algorithms that run at different speeds can have the same O notation. My assignment panic wouldn't have happened if I used an algorithm that was n log n, but that was just x times slower than my classmates. Now sure, faster is better. However, the difference between O(n) and O(x squared) is astronomical when you get to big data. And the difference gets so big that how much time in single iteration of the algorithm takes doesn't really matter. We're not trying to precisely calculate how long an algorithm would take so we can precisely compare each algorithm. Instead, the big O notation helps us answer the question, is this algorithm efficient with big data, or will it blow up with big data sets like my brute force algorithm did? And that is why big O notation exists and why it's useful.